Hello, everyone. Okay, let me just share the link. Would you please let me know if you can see the slides? Perfect. Okay. So just continue working on chapter 5 today. So I hope you still remember what we discussed so far in the last lecture about the importance of dimensional analysis and basically the idea of using this concept is to do some analysis for either a complex phenomena or in a design process. And this, dimensionless analysis is considered to be the third kind of, approach of making analysis for a fluid flow system. But I mentioned also last time that we can apply the same principles to many other subjects, right? And explicitly mentioned that you can use some of what we are learning in this chapter on in different type of design aspect that you are working on different kind of topics. So last time we talked about how can we determine dimensionless group that is representing fluid parameters, and we used Buckingham Pi theory to develop what we call it the Pi groups, and those Pi groups are characterized by a non-dimensional group that can represent different aspect of the physics in the fluids, right? And if you remember, I listed these tables for you last time, just presenting some of the very common numbers or non-dimensional number in the fluid mechanics subject, but you can extend this to many other parameter or dimensionless number in other topics. One of the very important thing I have to remind you about this discussion is we are not in the position of just selecting randomly those numbers and put them together without some understanding of the physics of the fluids. That's why those very common numbers that people develop in the past, and then they come up with some correlations between these some of the fluid phenomena that you are studying, as well as a function of these numbers, they end up with with some understanding about that what those numbers are representing to, right? So for example, if you remember, Reynolds number is considered to be the inertia forces over the viscous forces. So which means that if you have a phenomena in the fluid mechanics that is, there are some competing two forces in the phenomena. One is related to the mass and the inertia of these fluids versus the resistance and the friction viscous forces. So those can be represented by Reynolds number. And we went through a very simple exercises. How can we develop these with a systematic approach of using the Buckingham Pi theory? And we end up our lecture by summarizing what we learned in this topic. And some people were asking about, like, what will happen if I choose different parameter or the repeated variable is differently, and then I will end up with a different, different formula of these numbers, or different, a combination of these numbers. And we talk about this as, with an experience, with people are working a lot on the topic, they start gaining more understanding of how to select those parameters. And at the end, whatever number that you are creating out of this group, you can manipulate this number. And we mentioned few simple, approach to this, like, reversing the number, or, putting this number to the power of, a certain n, or we multiply by a constant and all these kind of things in order to manipulate this number to be similar to a very common used non-dimensional group that we always find in these different topics. And at the end, we said this is all going to be based on your experience. This is going to be all based on the amount of work that you are doing, in this. But the most important thing was, how can we minimize the number of experiments that we need to do in our lab, because those experiments will cost a lot of money, if we don't really consider the most important relations. So if we go and find out the effect of every single parameter on the other parameters, this might take forever or might take a lot of time and money to do this. So reducing the number of parameter into groups will help in this process. And in general, engineers will be deciding to design an experiment or design a new product or something like that. It's going to be a lot based on their experience, their way, or the skills that they acquired before in order to get like a good design or optimize the experiment that you need to perform. Okay. All this was an introduction to what we call it similarity and modeling. Okay. So today we're going to talk about modeling and similarity. So when we are talking about similarity, we are considering, for example, something called a model and a prototype, or a general full-scale prototype. And one of the very common sense, first step is basically applying what we call it the geometrical similitude or geometrical similarity. So if you are building, a ship like this in these slides. Okay, if we are scaling down this ship into something else, or like a small little model to be tested in the lab, we are expecting every dimension in the actual full scale, prototype is basically, with the dimension in the model, or the ratio between the dimension in the full scale versus dimension in the scaled model will be given by what we call it the scale. And this is what you did, guys, when you did for example, engineering drawing. So what you do is for example, you look at a certain machine and you select a certain scale and you draw this machine on a paper, or on a small scale type of of illustrations, right? So the first, in order to say that we have some kind of similarity between the model and the prototype, or the model and the full scale prototype, is basically a geometrical scale. Okay, so for example here, this L in the model, okay, and L divided by the prototype will be, let's say, for example, is 1/100. So now, can I use different scale when I represent all the dimension, or it has to be the same for all dimensions? Sorry, I'm speaking too much, but let's have a little bit more discussion here. So when I build a model, do you think any of these dimension in the model over the dimension in the full scale? Yeah, for all, right? So you cannot really use different scaling for part of the model versus the other part, right? So it's all the dimensions has to basically fulfill and satisfy the scale between the model and the full scale prototype. Okay, and this is what we call it geometrical similitude or geometrical similarity. So the first condition for you to test something in the lab that represent the full scale operation of the actual machine or actual device is to have at least, first step is geometrical similarity. Okay, the second one is you are testing something in the lab. Let's say, for example, a small little pump pumping fluid in a system, and this pump is representing, let's say, a huge pump that is, carrying crude oil, between like, cities in a pipeline, a crude, oil pipeline. Okay, so in this scale, like, in this case, how can you make sure that whatever you are testing in the lab and the condition that you are testing this model on is representing the actual performance? Okay, so the second important similarity that you have to make sure that it is satisfied is something called dynamic similitude. Okay, dynamic similitude or dynamic similarity, it means that basically all the forces acting on the model must be in the same ratio, right? It has to be a certain kind of scale. And of course, you are expecting the scale of the dynamic forces should be somehow related to the scale of the geometrical, right? So if you're building, a huge machine, and you're building a small scale of this machine, right? The forces acting on the model should be somehow related to the scale that you are building this model from, right? So condition one is the geometrical similarity. The condition two is the force ratio, or the forces, the ratio between the forces in the model and the forces on the prototype has to be somehow constant. It's the same thing, like all the forces in the model versus, or divided by the forces on the prototype has to satisfy the same kind of ratio. Is it the same geometrical ratio? Of course not, but there's going to be some ratio, but this ratio is constant. And it might be related, as we're going to see today. How can we relate those forces if we are scaling geometrically the model, by 100 or like 110 or whatever geometrical scale that we use? Okay, so one thing that we have to make a conclusion about these two, if we have like a geometrical similarity and if we have a dynamic similarity, okay, the condition 1 and 2 leads to what we call it the condition 3. And the condition 3 mean that appropriate dimensionless number must be equal. Okay, so once you are kind of, generating this similarity between the model and the prototype, geometrically and dynamically, right? So whatever non-dimensional number in the model should be equal exact the dimensionless number we have in the prototype. Okay, and this condition, or the this conclusion on point 3 here is very extremely important to the design of an experiment or design of testing platform for a new product or on a scaled product that you are testing in the lab, and making sure that it is performing the same way as the actual prototype will perform. Okay, so those dimensionless number will be the same, and in this case we'll end up with some relation that we have to find between the model and the prototype. Okay, so the requirement of the similarity between the model and the prototype is that the significant dimensionless parameter must be equal for the model and the prototype. And one simple example here, when we are talking about forces, we know forces is mass times acceleration. Okay, so now if I have the flow velocity or the forces in the model and the forces on the prototype, the ratio between them will be basically mass and mass times acceleration here, right? So mass times acceleration for the model and the mass times acceleration on the prototype, which is going to be equal constant. Okay, I mentioned last time that every dimensionless number that we listed in this table that I start the lecture with is basically representing some physical forces. So for example, flow around dams like this, okay, it is somehow, the physical model here it's a gravity forces and the inertia forces. So the ratio between the inertia or the mass flowing around the dam, the inertia of these flow around the dam, and the gravity, because gravity is considered to be, one of the major important forces that is driving the fluid in this case. So we're expecting to see something called Froude number, and the Froude number in these tables are representing inertial force, divided by the gravitational force. And that's why we said, okay, Froude number in a prototype has to be equal to the Froude number in the model. Okay, again, all this will be gained by the experience and the amount of work that you are doing in the fluid mechanics. The more you know about the actual phenomena or the physical phenomena, the more you will be easy for you to determine which dimensionless number we have to use. Sometime in the beginning, for like, first fluid mechanics course, we kind of helping the student to understand, what number to choose by indicating something in the description of the problem. So we talk about like gravitational force. So, gravity and inertia has to be related to Froude number. Viscous and inertia are related to Reynolds number, right? Well, I'm not going to go, everywhere and confuse you with so many numbers, but those are the most common numbers that we use in our first course of fluid mechanics. Okay. As I mentioned, like, for example, fluid in a pipes that has no free surface effect. And free surface mean what? Anybody remember what is free surface referring to? When we have a free surface, what does it mean? When you have a fluid in a free surface, what is free surface referring to? What is the condition at the free surface? Please help me. So, yeah, no, has nothing to do with shear stress. Not enclosed, yeah, but what is this referring? Okay, what is physical? Pressure is equal 0. Thank you. Right? Pressure is atmospheric. Okay, this is what meant by free surface. So what do you think about these, flow around dams here? Do you have a free surface? Do you see a free surface or not? Yeah, that's a simple question, guys. Do you see in the flow around this dam, you see a free surface or not? Yes. Anyone else? Everybody see this or not, right? Because this is atmospheric, right? So anything here is atmospheric. So the flow is moving like this, and this is open to the surface, right? So the flow in the river and oceans, and this is like, exposed to the atmosphere, right? But flow in a pipe like this. Do you have a free surface here in this pipe? Do you have a free surface in this pipe? Of course not, right? Because this is enclosed, right? And the pressure at any point here could be different, right? The pressure inside the fluids, in this pipe could be different, right? Which means that when we have a condition or have a problem, it doesn't have a free surface. And the fluid is moving in ducts like this, like, either gas or liquids, right? So those are like, Reynolds number. Same thing as if you have submarine, right? So this submarine here moving underwater, right? Again, the pressure forces here, the forces on this surface here is not a free surface, which means that also, there are some resistance, and this resistance will be coming from viscous, right? And there's going to be some inertia because this is the mass of the submarine moving with a velocity, right? So we are considering viscous forces and inertia forces, which mean, what we call it the Reynolds number, right? So those are the very, very common number that we use in our beginning of understanding dimensionless analysis. So you are expect like, fluids around bodies like this is considered to have a dynamic similarity when the Reynolds number in the model and the Reynolds number in the prototype to be equal, right? Okay, so let's work on an exam problem like this, just to give you an idea what is involved in this type of problems. He's asking you have a model, tests are to be performed to study the flow through a large valve, right? So you have a big, huge valve that is 2 feet diameter, okay, and carrying water at a flow rate of 30 feet cube per second. This might be like, a water distribution system in a city or something like that. And the main line that is like, more than 2 feet diameter. So you have a valve, installed in this pipe, and you need to test this valve. Yeah, you need to know, for example, at different flow rate, what is the pressure drop and stuff like that. If it's open, if it's closed, stuff like this, right? This is normally like, typical, experiment that will be required to do in a lab when you want to like redesign a new valve or design a new system and so on, right? Or if you don't, if you are actually a manufacturing company are making those valve and then you want to test these valve in the lab. Of course, you are not going to test the full scale, because the full scale is the valve will be installed in a city, like, main pipeline carrying water in in the city, which mean that in order to test these valve at a full scale, you have to really build a scale of a city in order to test this, or like a big huge pipe to test this. So what you're gonna do is you're gonna make a model out of this valve. And very important note here is telling you that the working fluids in the model is water at the same temperature as it's in the prototype. What does it mean? It means that this valve is in real life, in the full scale, is carrying water, and the model also will be tested in the lab for water. Okay, so just keep this in mind. So both fluids that you're gonna use for testing the model is the same fluid that is in the full scale prototype. Okay, is basically telling you a complete geometrical similarity exists between the model and the prototype. What does it mean? It means the valve that you are making in the model, right, looks like the same as in the prototype. However, like on the model inlet diameter is 3 inches. Okay, which means that the valve that is 2 feet diameter in the full scale, now we are getting a smaller valve similar to the other one, but now the diameter of this model is 3 inches. So he's asking to determine the required flow rate in the model, or the required flow rate needed to be testing the model. Okay, anyone can tell me how to start? Anyone? Model and R in geometrical which means that the diameter of the valve in the prototype, if you remember, it was 2 feet. The diameter of the valve in the model is 2 inch. Okay, so just make sure that this is the same dimension. So let's say this is 24. This is 24 inch. Okay. So the dimension, and you say in geometrical similarity, that means the scale here is D of the prototype. D of the model is 24 divided by 2. This is 12, right? Or 1 over 12. Is it 3 inch? Sorry. Sorry. Yeah, it's 3 inch. Sorry. Inch. This is 3, right? So it's 8. So I have 31 over 12. No, it's a 3 inch and it's 2 feet. So 24 divided by 3. Right? So this is basically our geometrical scale. So every dimension in the valve will be basically 1 over 8 of the the actual dimension in the full scale valve. Okay, now both model and using water at 20 degrees C, which means the fluids, right? Sure. Yeah, so whatever the ratio, just make sure that you are basically, you know which one over, like, you know, what is the scale, model to the prototype or prototype to the model. Just as long as you know dP over dm is 8 or dm over dP is 1/8, it's fine. Okay, now both model and prototype are using water at 20 degrees C, right? Both of them at the same, which mean what? What does it mean here? If both same density and what else? Viscosity, right? So U of the model equal U of the prototype. Rho of the model equal rho of the prototype, right? So which means that all the, you know, fluid here and the fluid there are the same, right? Okay. Now for, this is like, you know, geometrical similarity exists. What condition that you have to make sure that this is, you know, satisfied in order to make sure that you are testing the right condition? What other similarity has to be satisfied? Dynamic, exactly. So for dynamic for dynamic similarity, forces are the same kind of, you know, it has the same ratio, right? And for dynamic similarity along with geometrical similarity, this is lead to what? This is a valve. Very, like, you know, cartoonish kind of, you know, illustration here. The flow is going like this. So is the flow actually inside the pipe? Okay. For both to be dynamically and geometrically similar, what does this lead to? A geometrical similarity and dynamic forces, yes, okay, but you know the problem now, it's becoming very, we know that these forces will be the similar for dynamic, but it's in order to represent this in a you know measuring parameter, because we don't know what forces we're talking about here, right? I don't want to you know, make the problems very complex, right? But if you remember when we said we have a geometrical similarity and dynamic similarity satisfied, okay, you remember the third condition, appropriate dimensionless number should be equal. Okay, what do you think, which dimensionless number we should use for this you know, for this problem? Reynolds number, right? So we can say, for example, in this case, Reynolds of the model should be equal to Reynolds of the prototype. Okay, and this is basically will lead to your solution for this problem. Okay, so in this case, Reynolds model equal Reynolds of the prototype. Reynolds, we know, rho v d over mu, but all this will be model. Okay, this will be rho prototype v prototype d prototype mu prototype. Okay, and it has to be equal exact, because both should be exact same, because both has to be dynamically similar and geometrically similar. By knowing that the fluid is the same, in this case, that means this is basically the same, density is the same, right? So density is the same, viscosity is the same, because fluid is the same at the same temperature even, right? So in this case, what can I get out of this? I can say that the velocity of the model, I can take this on the bottom here, velocity of the prototype equal to d prototype divided by d model. So whatever velocity of the, you know, of the fluid inside the model divided by the velocity of the, you know, the fluid inside the prototype has to be the same ratio here, right? And I know this ratio to be what? 8, right? Which means that now the velocity has to be like this, right? So, okay, but in this problem, the velocity is not given, it's just given flow rate. So what do you think about another important relation that we can get for the flow rate and the velocities? Q, right? So I can say, for example, in this case, this is, let's say, equation 1. Also, Q of the model over Q of the prototype equal what? Q model is area model, velocity of the model. Q prototype is area prototype, V prototype. Okay. Tell me, what is the area? Okay. What is the area in the model and the area of the prototype? It has to be related to what? Q is not rho AV, right? Q is only area times velocity. Yeah, but area is 8, it's square, right? Because basically the area is, if we imagine like, whatever the area here in the pipe here will be pi over 4d square, right? So the area here has to be what? Let's say pi over 4d model square, pi over 4d prototype square, right? And this is time V model. And again, this is time V prototype, okay? So this is, okay, D model or D over prototype. What is that giving you? So D model over D prototype is 1 over 8 square, okay? And from equation 1, you have a V model over V prototype, right? Because you have these V model here divided by V prototype, and it is 8 divided by 1, okay? Which means that this is basically what? Q of the model over Q of the prototype end up with 1 over 8, okay? So if I know a flow rate in the model, I should find out the flow rate in the prototype. Or if I know the flow rate of the prototype, I have to test the model at the flow rate in the model based on this relation, right? So if you can see that, so I know given here Q of the prototype, what is that? Q of the prototype, the flow rate in the actual valve. The flow rate in the actual valve is 30 feet cube per second. So I can find out what should be the model tested at what flow rate, right? So I can say that basically in this case, this is 30 feet cube per second. Okay. So in this case, Q model, Q prototype equal 1 over 8. So Q prototype is 30. So therefore, Q of the model here will be 1 over 8 times 30 feet cube per second. This will be 3.75 feet cube per second. What is this telling you? It's just telling you that when you are basically scaling down a valve that you want to test in the lab, okay, you don't need to run the same flow rate, right? Because it's a smaller scale, right? So you scale down, right? You scale down these valve geometrically, and you scale it dynamically. That means you only need 3.75 feet cube per second to pass through the valve to test it. So maybe you want to measure pressure, you want to measure forces on the valve and all this. You want to test the material, for example, how the material will sustain erosion or whatever, right? You don't need to run, the full scale flow rate. You just need to run for this model right? If you scale it 1/8, because the geometrical scale here is, yeah, it's 1/8 or the 8, right? You scale it by that much, that means you get the flow rate to be that much. Okay. I think I have another problem here. Let me just add this. How about, okay, you know that in order to do this, like, I'm not sure how many of you have seen experimental facility in the lab that is, if you've seen, like, the testing in your fluid mechanics lab, right? So, like, you small scale benches and small little, valves and piping, right? So you know that, right? It costs some money to run this whole setup. Imagine now you need to run that much flow rate. This is very high flow rate, right? So 30 feet cube per second, that's huge, right? So how about if you 3.75 feet cube per second? How about if you have a limitation in your lab? So let's add another problem here. If you have in your experimental setup at 1 feet cube per second. So imagine now you are building. The first two conditions are met for geometrical, mean that every dimension is okay. I'm not sure, Trevor, if I understand what you're talking about. Geometrical and dynamic similarity, yes. Q model and Q prototype. Yeah, we got this ratio between the velocity based on the dynamic similitude. Okay, QB and QM, it's like it's a ratio, right? It's a flow rate of flow rates, right? This is not have nothing to do with, you can decide to divide Q over Q, right? We're just trying to find out this ratio as a function of a limitation in the problem. The limitation in the problem that any velocity in the model and any velocity in the prototype has to be 8, and any dimension of the model over the dimension of the prototype has to be 1/8, right? So you can use whatever other parameters ratio, but you have to satisfy these two conditions for dynamic and geometrical and find out this ratio. Okay. To the flow rate, can handle. Okay, so Layan, is that the answer to my problem here? Yes. Okay. So what options here? We have one option here is, what do you think about this? Reducing the diameter. Is that a good approach? No, I think, Trevor, you are confused about this. Let's discuss it at the end of the lecture. If you okay. So one of the approach is to scale down. So one solution, scale down the model. Okay, and how can I scale the model in this case? You see here, it looks like I am gonna be, this will be missing because I don't know, right? And now I can say, for example, here, the function of the V model of the V prototype will be the scale, right? So in this case, I will start from this equation. Okay, so and I put, like, V d over d is 1 over scale, right? And basically I can consider the scale to be x, right? So scale mean 1, instead of like 1 to 8 is 1 to x, right? And then I can just like, go backward from this equation, right? And find out what will be the scale. By applying, you're gonna have two equations now. One is a dynamic similarity and one is, the geometrical similarity, okay? Okay, how about other options? Downscale the model, so another solution. And let me tell you that, you have no options, let's say, for example, to scale down the model because, this company are asking for, yeah, nice, Matthew, right? Change the fluids, right? You can play with the fluids, right? So imagine you have a company and the company is making those valve and telling you, okay, I can do a model, I can generate a model for you to test it in the lab, but the smallest I have is 3 inches, okay? I cannot get it, I cannot get it smaller than this, or it's going to be, if it's smaller, it's going to be like, the material will be different. So it's going to be complicated, other issues, right? So another solution, if the scale is maintained, okay, you can change the fluids. Okay, and in this case, what you're gonna do is like basically in this equation, okay, you might have like density and viscosity, and you have the dimension here. So in this case, instead of like V model over V prototype is equal 8, you're gonna end up with this 8 here, and then you have the ratio between the density and the viscosity as well. So the velocity ratio will not be equal 8. It might be a little bit, smaller value because, you are using, for example, heavier fluid, okay, in this case. So can I use like, different viscosity, maybe higher viscosity and higher density and so on, okay? So you can have many problems on the same type of analysis. And this is what happened in the real life. You are being asked to do a design of an experiment and stuff, and then you start, getting some parameters. Some of them are related to the cost of the material and operation of the experimental facility. And in order to maintain this limitation of cost and other thing, you might have to take decision about like, oh, I'm gonna, use a different fluid for that. Oh, I'm gonna use maybe a different temperature, right? Same fluid, but maybe I will just, increase the temperature in order to, change the, viscosity in the fluid in the model versus the actual viscosity in the prototype and so on, right? It's going to be all related to a dimensionless group that is equal between model and the prototype. All the, again, we're not opening the complete scaling analysis in the fluid mechanics subject. This is just like, the first layer that we need to understand in this, right? So it might be much more complex kind of, phenomena that cannot be captured using the analysis that we are doing, but this is at least the first step to this kind of, thinking process about like, modeling of an actual prototype for scaling. Okay. So please think about these two questions and like, try to, do an exercise by yourself, like, if what will be the type of fluids, can be used, or what will be the scale that you can get if you're going to scale down the model. Okay, another type of questions, in the past exam as well, right? I'm sure that you're going to solve some tutorial problem from the textbook with the TA. Those are problem maybe not similar to the one in the tutorial. That's why I'm actually getting them solved here in the lecture. So imagine I have an explosion like this. An explosion occurred in the atmospheric when an anti-aircraft missile meets the target as shown in the figure, okay? So a shock wave, and this is what happened once you are like, have an explosion. the temperature goes like very high, and then the pressure basically change, suddenly, right? And the idea of the explosion is the very rapid change. Okay, so the very rapid change in the in the fluid around, or the the surrounding environment around the bomb, right? So what will happen in this case? It will create like a shock wave. Shock wave mean, between before the wave and after the wave, huge drastic change in the pressure. So the pressure inside the core of this explosion will be like much higher compared to the pressure on the edge of the shock wave. And now as this wave is going, of course, like the effect of this delta B will change. So the location of the explosion will be the maximum pressure increase. As you go, the pressure will be basically decreasing. So so a shock wave, also called the blast wave, right, spread out radially from the explosion. The pressure difference across the blast wave delta B, so this delta B is across the wave, and the radial distances R. So from a certain point, from the center of the explosion to the point where this delta B is, this is what we call it the radius, or the radial distance. And from the center are a function of the time. So with time, of course, this is like, these pressure waves is traveling with time. So, and the radius is increasing. And also they are function of the time, function of the speed of sound. Okay. So speed of sound here is C, and the total amount of energy E, right? So the total energy is basically E released by the explosion. Okay. We first asking you to generate dimensionless relation between delta B and the other parameter, and between R and the other parameters, and then is asking you for a given explosion, if the time since the explosion is doubled and everything else is equal, what will be the factor of delta B, or how much delta B will be decreased. Okay. So let me ask you first, okay, in order to generate this dimensionless group, is giving you all the information. You have the difference of the pressure delta B. So delta B will be the main parameter. What other parameters I have? So delta B, this is the main parameters, equal function of the time, speed of sound, and the energy. Anything else? Guys, anything else? Oh, the radius, sorry. Okay. Okay, so what else I have here? Okay. So let's discuss this. So people saying we have to put the radius here. Some people, are silent. And delta B is function of T, C, and E. This is my call, and this is your call. Okay, which one? That's the only trick in this problem. Okay, he's giving you that basically, if you read the problem, the pressure difference across a blast wave and its radius R, okay, from the center are function of time, speed of sound, total amount of energy released by exposure. Okay, Jacob, why? Because this is actually B, delta B at certain R. Okay, he's telling you that pressure wave and its radius, right? So which means that this delta B at a certain R, right, is function of the other parameters, because, you know, R is not, delta B is not changing with R. Delta B is actually at any R is that much, right? So we're saying that this is delta B and R are kind of one variable, right? So, and we call it the pressure difference at any position R, okay? So which means that in this case, this is basically the condition. So delta B here is pressure difference at radius R. Okay. So how can we find out, you know, let's first say, okay, how many groups here? Okay. So what is N here? How much M here? 4. Amazing. Okay. And now if I put like delta B and T and C and E, and I put the dimensional, right? It's going to be like delta B is M, L minus 1, T minus 2. T is T, right? Speed of sound is L, T minus 1. Energy is M, L square, T minus 2. Energy is force times distance, right? So all this, right? So what is M here? What is M here? Anyone else? You guys, everybody? Okay. Everybody remember? Okay. So this is, we see M, we see L, we see T. That means we see all the 3 main, 2. Okay, 3. Thank you. Okay. So we have 3 here. So number of buys here is what? By group. Number of buy groups. Opportunity for you guys to participate in this exercise. You didn't study, right? It's 1, right? Because it's M, it's N minus M, right? So it is 4 minus 3, it is 1, which means it's by 1. So at the end, the maximum number of group you create is by 1, just by 1 by. So what is this equation will be converted to? Remember, by 1 equal function of by 2. Now, what is the equation? I have to write it down. M is the number of, the dimension, the basic dimensions, right? In all of the parameters. So basic dimension mean M, L, and T. The maximum of M is 3, right? You see M in these, that means it's 1. You see also L, that means now we have 2. You see T as well, that means you are seeing the 3 basic dimensions. So that's why M is equal to 3. Right? Okay. So by 1 is, that was the only trick in this exam, like, just like, so the by 1 has to contain the main variable, right? Okay, but remember in the past, in the last 2 exercises we solved last time, we developed like by 1 equal to function of the other by's, by 2 and others, right? Here we don't have another, right? It's only by 1. What does it mean? If you have only exactly presence, right? Amazing, excellent, right? So by 1 is constant because there is no other groups, right? Which means that whatever group that you are creating here is equal a constant. Okay, So we can do the same thing. We can, if you remember, by 1, in order to generate this, we say that basically delta B times the other repeated variable. You have no choice. The others, 3 repeated variables, because is the number of repeated variables is equal m. So m here is 3. That means you have to select 3, which has to be the other 3, right? So it's going to be like t to the power a, and c to the power b, and e to the power c, right? And we do the we do the exercise that we did last time. Okay, we get the m to the power 0, L to the power 0, and T to the power 0, and then we can get those numbers. Okay, I'm sure that you can do this. So A here is going to be minus 3. Sorry, this is 3. B here is 3, and C here is minus 1. So what is this telling you? That telling you that this by 1, it is basically delta B, okay, T cube C cube divided by energy. Okay, and this will be equal constant. So in this case, I can say, for example, here delta B is equal constant times E divided by T cube C cube. So this is a relation that we can get out of that. Okay. So, and again, this delta B at any R, at any radius, going to be R. Now he's asking in the second part of the question, for a given explosion, if the time t since the explosion is doubled, all else being equal, what should be delta B, decreased? Okay. So if the time is doubled, okay, what will be? So what can I do here? Exactly, right? So in this case, it's everything else is constant. That means the speed of sound is constant, the energy is constant. That means it is going to be delta B. So delta B1 over delta B2 is equal, the constant will be, divided. So energy okay. So this is constant. That means it is T2, and T2 is doubled T1. Therefore, delta B1 over delta B2 is equal to 8, right? So in this case, I can find out delta B2 is 1 over 8 of delta B1. So for the first, let's say for the first second, the pressure that much. For the second, or the double of this, time. So second 2, the pressure reduced by 1/8. And the more that doubling the the time, the much decrease of this pressure is. Yeah, T2 is double. Yeah, so T2 is equal to T1. So if you put this, so that means, yeah, it's gonna be like 2 T1 cube over T1 cube. That is basically 8. Okay. Any questions? we can conclude the relation from our by equation. Yeah, this is what we did, the by equation. Yeah. Is that what you mean? Like, looking at this? Yeah. By is constant, so you can say that. That's fine. For this problem is straightforward because other parameter is constant and stuff like that, right? But for other problem, you really have to, go step by step like this, just like making sure that you are satisfying every change in the problem. Okay. Any other question, guys? Is it clear? Like, is it? I know we are just focusing on the most important pieces of this topic that will benefit you and going forward with your design or your calculations and stuff like that. So I hope this is useful. I consider this is very important to general design, problems, or people working in the lab and doing experiments. The last page. This one. Yeah. Any other question, guys? I actually concluded my lecture for today, so we might finish early here, but I will stay until everybody's question. I guess some people were confused about something in the beginning. Please stay around and we can discuss it if you want. Any questions, guys? I can stop the recording so you can, we can continue our discussion if you want to speak out or discuss something.
Professor?
Yeah.